Hello everyone, and today we will be talking about internal energy. And you'll recall that internal energy is given the symbol U, and that we can describe total internal energy as the heat plus work. But if we take a step back, we can also summarize the total energy of a system as the energy of translation and the way that that applied using kinetic molecular theory, the energy of rotation plus the energy of vibration and the energy of electronic transitions. And I'm forgetting the plus right there. And for translational energy, we found that the kinetic energy of a particle is the integral of the work from a starting velocity equal to 0 to a final velocity Vx. And we summarize that as delta K equals W equals the force times that displacement. And if we went ahead and integrated with respect to velocity from 0 to some final velocity, we found that we saw the relationship as being equal to 1/2 mv squared, or the kinetic energy. As we continued that conversation about translational energy, we found that each translational degree of freedom was equal to 1/2 kT for an individual atom, or was equal to 1/2 RT for a mole of a particular gas. And so if we wanted to consider all translational degrees of freedom, we would find that we have 3/2 kT for X, Y, and Z, or 3/2 RT for X, Y, and Z. Of course, that being for a mole of our gas. And if we need to, just to recall, we'll go ahead and draw our Cartesian coordinates and show that we can in fact move in X, Y, and Z. And this ability to move is again a way to store energy. And then we can begin to have a conversation about rotational energy as well. But let's at least summarize that U, or this internal energy, if dealing with translation, would be equal to 3/2 RT. And so let's keep that in the back of our head. The storage of energy in the degrees of freedom of a molecule is summarized with the equipartition function. Or excuse me, the equipartition theorem. I apologize. And basically it states that each degree of freedom, which we'll summarize as DOF, can store 1/2 kT of energy. And so, as our example, which we commonly use here in Chem, is for N2. And we would show that for translation, we've got 3 degrees of freedom. For rotation, we've got 2 degrees of freedom. The rest of that F needs to go in there. And for our vibrational degree of freedom, we would have 1 DOF. And if we wanted to look at the degrees of freedom for N2, what we would end up using, again, if we want to draw a picture over here in the corner, in our Cartesian coordinates, and we've got our N2 molecule, the only way that it's going to vibrate is by stretching along the internuclear axis in such a fashion. And when we want to calculate this, we can say that the degree of freedom will be equal to 3n minus 5 for a linear molecule, and would be 3n minus 6 for a nonlinear molecule. And as you can imagine, with n equaling 2, 3 times 2 minus 5 equals 1, which is consistent with a linear stretch of n2. So dovetailing from this idea of storing energy within degrees of freedom is heat capacity. And again, we can have our ideal gas, whether or not that's N2, or that could be a spherically symmetric helium atom. Heat capacity can be described as the ability to store energy as heat inside of a material. Mathematically, we can say that the heat capacity is equal to the heat divided by its temperature. Here we have heat, and occasionally you'll see capital Q or lowercase q. Here is the temperature and our heat capacity. The heat capacity of high is relatively large for water, as opposed to something like aluminum foil, which has a slightly lower heat capacity, and you can see that with the amount of energy it takes to heat up water, or how cool aluminum foil will be to the touch after you've quickly taken it out of the oven. And you'll notice that heat will be in joules as our universal energy metric, and temperature is in Kelvin. So heat capacity should be in joules per Kelvin. You can also quickly recognize that the heat capacity would also be equal, or times its change in temperature is equal to the heat of the system, just by a simple algebraic rearrangement. But let's imagine now that we want to look at the heat capacity, the ability to store energy. At constant volume. And this is even before we fully discussed the first law. But what we would say is that C sub v, and you'll notice that that sub v is there for constant volume, is equal to the partial derivative of the heat as a change of temperature at constant volume. And we can also be holding the number of moles constant, so that would be C sub Vm is equal to some change in Q as a partial derivative of t as we're changing phi sub v m. Now what we know from our past discussion is that for an ideal gas, and in this case it's a monatomic gas like helium, in those translational degrees of freedom, that the average energy should be equal to 3/2 kT or 3/2 RT for a mole of our gas. Now with this energy storage for helium being equivalent to 3/2 RT, we can say that the heat that's being stored is 3/2 RT. And now let's put that into our partial derivative. So C sub Vm is equal to the partial derivative of 3/2 RT as a function of T, a constant volume, and the number of moles. And you'll notice if we took the first derivative with respect to T, that T would go to 1, and that our heat capacity would simplify to 3/2 R, which is equivalent to 12.47 joules per Kelvin mole for an ideal gas. And in this case, this is a monoatomic gas. And just as a quick refresher for our math aside, in the case of that partial derivative, let's recall that our partial derivative is signified by our swooshing d, while our full derivative is represented by our regular d. And so if we were to do a quick example of a function with respect to y, where we are doing a partial derivative with respect to y on a function of 3x squared y squared, we are only applying or only doing work to y itself. And once we've applied that derivative, we're going to get 2 times 3x squared y 2 minus 1 to then yield 6x squared y to the first power, or 6x squared y. And the same thing will apply time and time again as we do partial derivatives to any of these functions.